Welcome to BKW Physics. I'm Mr. McConnelly, and today's topic is polarization. Polarization. And I want to start with this demo here. I'm using an old-fashioned projector to shine some light up on the board. And I have some material here, which is basically what you would make sunglasses out of. But these would be polarizing sunglasses. So I claim that right now I am polarizing the light. The light that's shining through is polarized. And you're like, I don't know what that means. It just looks darker. Okay. Well, what I'm going to show you next is that you can take another one of these. Now notice this one just happens to be a different shape. But they're the same thing. You can take another one of these and notice that, they're about the same darkness. It's blocking some of the light. If I overlap them, notice it might get a little bit darker, but not that much. But here's where it gets interesting. If I have tabs on these, you can probably see I put tape tabs so I can tell which way is which. If I take and I start rotating this, notice the rotation, what do you notice about the overlap? It's starting to get a little darker, and in fact, if I rotate it at 90 degrees to the way I started, it's black. You can't see through it. It's blocking all of the light. There's no light that can pass through this. And this proves, now to you right now, you're probably not convinced, but this proves that we're polarizing the light. I want you to think of polarizing like this. Light waves are traveling along. And you basically, when you polarize something, you block all the waves except the ones that are parallel to the polarizer. So let me kind of draw it on the board. If you think of this as having bars, then which way is the light going to be able to pass through these bars? Well, the light waves are going to be able to pass through, they're going to sneak through between the bars this way. The light waves that are going this way, what's going to happen to them? They get blocked. The bars kind of stop them. Dong, and they bounce off. So this process of blocking the light so it only occurs or moves in one direction is called polarizing. This is polarizing. So is this one. Now, right now, which way do you think this one is polarizing in comparison to this one? And I see some people giving me the motions. This polarizer is polarizing perpendicular, so you're blocking all the waves that are this way with this one, and you're blocking all the waves that are this way with this one, so you know what you're left with? Well, the light's not going through because you're blocking all the waves. Now, as soon as I start to turn it back, I turn it back that way, erasing these lines. Now I'm only blocking everything in one direction, so some of the light's still going through. Now, how is this useful? I want you to think about this for a second. How could this be useful? When you buy polarizing sunglasses, you have a goal in mind. You want to eliminate glare. Okay? So if you're a person that goes fishing, when you go fishing and you get out on the water and you're sitting in your boat and the sun is shining because it's a nice summer day, the light will be hitting the water and hitting you in the face, and you will be squinting all day long until you have huge wrinkled, sunburned squint lines on your face. That's what happens if you're out fishing. If you buy polarizing sunglasses, they don't just make it darker out, which they do make it a little bit darker, but they don't just make it darker, they block the light. So let's envision, I'll do a side view for the camera, that the light is hitting the water and then coming at you like this. Which way do you need the bars in the sunglasses? Right? If the bars, those invisible polarizing bars, if they're in the sunglasses this way and the light comes up, you're going to block the light. And you're not going to see the glare. That's what polarizing does for you. Okay? That's just one example. Now back here I have a visual. And I'm going to use a snaky And the first thing we're going to do is, if we can have our assistants, you hold both these meter sticks like this. Don't clamp on it. Leave a little bit of space, okay? But hold still. And then, if you can back up, I will send some waves, and these waves will pass right through. Notice that the meter sticks are really having no effect. If I send a pulse down, it goes down and back. It's not affecting at all. So this would be a demonstration that a light wave, I know in this case it's a snaky or a slinky wave, but a light wave is traveling and the polarizers are parallel to the direction of the wave, so it doesn't do anything. The wave just goes right through it. But if we take these, now can you stand them up on end like this? And you guys just kind of, one of you hold kind of high and one of you hold kind of low. Okay, now we're going to try to send the same wave down and watch what happens. What's happening? When the wave gets to the polarizer, what's it doing? It's just canceling it. It's not able to pass through, so what happens, this is like when you have your polarizers at a perpendicular to the way that the glare is. So the light comes down, it can't get through, and it's just eliminated. You've eliminated the glare, and you have polarizing sunglasses. Now, in the olden days, polarizing sunglasses cost a lot more money than regular. Thank you. You can just drop those down now. But at this point, when you buy polarizing sunglasses, you can go to Walmart, Kmart, or any big store and buy them for, let's say 40 bucks. You can get a good pair of polarizing sunglasses that will work excellent for you. In the olden days, it was just really expensive companies. So if we spin back to the board for a second, I wrote a little syllogism here. Polarization. If light can be polarized, did I prove that it was polarized with the first demo? Yeah, because I showed you how we block the light completely. And only transverse waves can be polarized, because I want you to think about that one for a second. If we had sent a longitudinal wave down that snaky, and we probably should to prove that. So spin back to the back again. Assistants? Hold that for a minute. Now a longitudinal wave, if I send a longitudinal wave, in other words I pull some of this and I let it go, the longitudinal wave passes right through. Let's hold the polarizers, the quote polarizers, the other direction, and I pull it back and I send a longitudinal wave. What does it do? It passes right through because you're still getting it at the other end, aren't you? Okay, so you can't polarize longitudinal waves. They just sneak right between the bars. So back to the front. Thank you. If light can be polarized, we showed it with the demo in the front, and only transverse waves can be polarized because the longitudinal ones seem to sneak right through, then light is transverse wave. This is kind of just something that can help you remember that light, electromagnetic waves, light, are transverse waves. So for today, that's polarization.